So here's a really quick example, just showing how we apply Gauss's law for electric fields. So in this exercise, we're told that we have a charge that is distributed uniformly along the z-axis, and it has a density of rho L0. So to kind of visualize what this looks like, we're going to have this image here. So that charge is going along the z-axis right here. So it's uniformly distributed along there. And so they want us to use Gauss's law for electric field. So we recall that Gauss's law for electric field is the integral over some surface of the displacement current vector dotted with the surface area vector. And so that's over the entire surface. And that's equal to integrated over some volume, the charge density over that entire volume. So in this case, we also need to make use of the fact that the relationship between the electric field, which is what we're looking for here, electric field intensity, that's equal to displacement over the permittivity. So we're assuming free space in this case. So if we break this down, so looking at this equation, if we were to integrate the charge over the entire z-axis or across this line, then this would just end up being L0 over the whole length of the line, L. So that's what the right side of the equation reduces to. On the left side of the equation, again, we'll have d, and then this will be times just the surface area of a cylinder. So we're defining a cylinder around this wire. And so the surface area for a cylinder, we recall, is just 2 pi RL. So now if we solve this for d, we'll have d is equal to rho L0 L over 2 pi RL. And so the L's cancel out, so the length really doesn't factor into this. And then we recall this relationship here, so E is going to be equal to D over the permittivity. So in that case, we'll have the charge density over 2 pi R epsilon naught of the permittivity. So this would be an expression to describe the electric field intensity of a charge evenly distributed down the z-axis. So you can see this is a factor of R in the denominator. So as you move further and further away from the wire, the electric field intensity will continue to decrease. So the closer you are to the wire, the more intense the electric field. And this should make sense. I mean, it should be intuitive that would be the case.